Right. Thanks, Xiaoji. So yeah, as he mentioned, feel free to ask questions. I will have built-in points, where I pause that are like natural stopping points for questions as well. So this is work with my advisors, Pradeep and Andrej, which we will be presenting at ICLR this year, which presents a formal analysis that shows that invariant risk minimization and some of these other objectives really don't accomplish what they were intended to accomplish. So consider the following out of distribution, the following binary classification problem. We have maybe images of cows in a meadow. And if you've seen this setup before in out of distribution generalization, you might be expecting camels. But I'm a little contrarian, so we're going to go with astronauts in space. And despite having not seen this exact example before, you're all excellent at out of distribution generalization. So you probably know what's coming next. At test time, we see an image of a cow photoshopped onto a space background. So it's clear that the space background is very strongly correlated with an image depicting an astronaut. And as a result, we might expect a classifier to sort of learn, okay, space equals astronaut. But in reality, it doesn't make the picture depict an astronaut. And so this sort of heuristic sort of only works just because of the way that the data was generated, and we wouldn't necessarily expect it to generalize in all possible situations. So this is sort of like a silly example just to give like another instance where this actually happens in the real world. Ribeiro et al., they did this study where they trained a deep neural network classifier, and they presented it with this image, which is a husky. It's a type of dog, but of course it looks quite similar to a wolf. So this image was misclassified as a wolf, and that's sort of understandable. You might expect a human to make the same mistake, but then they used some explanation techniques to basically determine what aspects of the image were contributed most to this misclassification, and they found that actually the elements that the classifier was paying attention to the most for this prediction was the background. So it saw the snow, and since wolves are more often depicted on a snow background, it was like, oh, it must be a wolf. So it's clear that in practice, this is actually happening, that these deep classifiers are using these correlations, which are not actually, in a sense, the correct features to be looking at. And so this raises the obvious question, how can we train a classifier to sort of not fall prey to this problem? And in particular, these correlations won't necessarily hold at test time. They could be reversed. If someone photoshops a space background onto a cow, we don't want our classifier to say, oh, it was an astronaut. So I'm going to present as part of background. This is a work by Peters et al. From about 5 years ago that proposes this algorithm called invariant causal prediction. Just as a preface, this is sort of like a formal overview of this idea. It will tie back into this idea of out of distribution generalization, and we'll see how in a moment. So here's how invariant causal prediction works. We're going to assume that the data is generated by some structural causal model. So what this means is that maybe there's some directed acyclic graph which describes how the covariates and the target variable y are generated. And in particular, we're going to assume that each node is generated as some sort of functional form of its direct parents, and then some additional exogenous noise epsilon. So this is a pretty typical assumption for like causal inference, causal discovery. What makes invariant causal prediction sort of what sets it apart is it has an additional assumption, which is that the data can be partitioned into environments. So what does this mean? We're going to assume that the entire training set can be partitioned into sort of sub data sets, each of which is drawn from an environment. So what is an environment? It's, as I mentioned, it's going to be a subset that has the same structural causal model. So you can see each of these environments has the same DAG structure, and we will assume that the functional mechanisms are also constant. But each environment has a distinct intervention on these covariates. Okay, so what is an intervention? An intervention is an arbitrary modification of the distribution of some of these covariates. So if you're familiar with the do calculus of Judea-Pearl, it's basically this idea that you can set a particular covariate to be whatever distribution you want, but all the other functional mechanisms in the structural causal model remain unmodified. So here in this image, we've depicted these interventions by these hammers. So for example, in environment 3, an intervention might cause covariate X4 to take an arbitrary distribution, but then the mechanism by which Y is generated as a function of X2 and X4, that remains unmodified. So why is this a useful assumption to be making, that the data can be partitioned in environments this way? Well, if you'll notice across these environments, the key observation is that if we assume that Y has not been directly intervened upon, then this sort of functional mechanism by which Y is produced as a function of its parents does not change across environments. Even if we intervene on the other nodes, this is invariant. So put a little more formally, this means that the distribution of Y given its parents is invariant across environments. And this means that if we train a predictor which only uses the direct parents of the target variable to make its prediction, it's minimax. So in this context, what minimax means is if we were to assume an adversary who is allowed to perform an arbitrary intervention at test time, so we could observe some other environment which has interventions, our predictor's predictive ability for the target variable would not change because we are using this mechanism which does not change across environments. In contrast, if we were to learn a predictor which uses a non-parent, then there would exist an adversarial intervention which could cause it to fail pretty much arbitrarily. So as an example, if we were to train a predictor which would use the covariate X5 in predicting Y, then in environment 3, this intervention on the node X4 would sort of sever the functional mechanism by which X5 generates Y. And so it could arbitrarily modify sort of the information that X5 contains about Y. And this means that our predictor could be made to fail arbitrarily poorly. So as an example, sort of like tying this back to our like silly example of cows versus astronauts, you might expect that an intervention would be like someone going in with Photoshop and changing the background, right? This is an intervention which doesn't modify other aspects of the image, but you can sort of set the background to whatever you want. So it truly is arbitrary. And to sort of further tie this in with the example that we've been considering, imagine that at training time, you were training on cows versus astronauts. So again, we have this structural causal model, which describes how our data is generated. And we might expect one covariate is the presence of a tail, and another covariate is the presence of black and white spots. And this gives rise to whether or not the picture depicts a cow. So there's some nuances here with regards to causality versus anti-causality. Like, is it the tail that makes it an image of a cow, or is it a tail because the image has a cow in it? We're sort of brushing that under the rug just for the purposes of illustration. So you could imagine that if the image depicts a cow, then it's much more likely that the background would contain grass in it. And a neural network trained on this might be expected to sort of infer backwards that the presence of grass implies that the image contains a cow, and sort of use this information flow, which it is informative, but you know, it's a problem, and we'll see why in a moment. If at test time you observe this new environment, which again is the same structural causal model, but this time there's this hammer intervention which uses Photoshop to place a space background on this cow. Now our classifier, which uses this information, it sort of is blocked from making this meaningful prediction. And in particular, it could be made to have basically zero accuracy by swapping the backgrounds. On the other hand, if we sort of follow this idea of invariant causal prediction and uncover the direct parents, we can see that regardless of the intervention, as long as the label itself is not directly intervened upon, our prediction is sort of minimax optimal. And in fact, you might imagine that if we were to intervene on the presence of a tail and the presence of black or white spots, etc., at some point the image would cease to be a cow, and our predictor would correctly pick up on that, right? So it is in a sense making the prediction using the correct features that we as humans might expect it to be using. So this is the general idea of invariant causal prediction, and it works really great when we have fully observed features. There are provable methods for this. When we observe data, you know, these covariates and this label Y, we might not directly observe the DAG structure, but there are lots of existing algorithms for provably uncovering the structure, and invariant causal prediction takes advantage of this, and there's lots of follow-up work that considers, you know, what happens if the functional form is nonlinear, and there's a rich literature of this provable causal prediction. On the other hand, we might consider what happens when we don't directly observe these covariates. It's obviously a much more difficult problem. In particular, if we assume that they form these sort of latents, which then are passed through some complex generative function, we have some generative model of the data. And as a result, instead of observing the covariates, we observe this extremely complex high dimensional image with a label. It's not so clear how to uncover the correct structure here. And so the techniques for invariant causal prediction don't directly transfer. So this raises the obvious question: how can we sort of identify these features who are invariant with respect to the target and will allow us to sort of generalize in a minimax sense, even when the covariates are latent and we don't directly observe them? So this is an open question. It's recently gaining traction, this research direction. So just to be clear, this talk does not attempt to answer this question. This is sort of the basis for a recent line of work with several objectives that have been proposed to solve this problem. And in this talk, I'm going to be showing that these existing objectives really don't behave in the way that we expect them to. All of these proposed objectives are intended to uncover this sort of invariant predictor that will behave well. And we pose a formal latent variable model, and we formally prove that solving these objectives rarely, if ever, really ensures doing better than just standard vanilla ERM, which, as we've seen, can really fail pretty catastrophically in practice. So this is like the primary background of invariant prediction. So I think this is a great place to pause if there are any questions about this so far.
I have a small question. So how do you usually determine these graphical structures? Because I know, like, for instance, they are in practice kind of hard to determine.
Yeah, so this is something that has been worked on for decades, and it typically involves assuming non-Gaussianity or taking advantage. It has to do with like the factorization of the joint distribution, right? If you assume that y causes x, then you can sort of model p of y and p of x given y. There's lots of different approaches to this. It's sort of an orthogonal approach to, or an orthogonal question to this question of invariant prediction. It's
okay. So you're just like illustrating, like basically the intuition behind this.
Yes, okay. Exactly. Yeah. Any more questions?
So I guess data augmentation in deep learning, could we think of that as a method of trying to learn invariant features?
Yes, I think that that's something that's currently, there's work being done to sort of formalize that intuition that augmentation is sort of inducing invariance to the correct features. Absolutely.
Cool.
Okay, so here's the basic outline of the talk. I'm going to present invariant risk minimization, IRM, and some of the, I'll also briefly mention some of the variations that have been proposed that try to solve the same objective, but like in a slightly different way. Then I'll present the latent variable model that we study in this work, which is meant to formally encode some of the sort of intuitive assumptions that are made by these works in like these works make sort of informal assumptions, and we pose this model to strictly and formally encode these assumptions. And then I'll present our formal results, which basically show that these objectives most of the time really don't do better than ERM. Okay, so beginning with invariant risk minimization, this is an objective that was proposed a few years ago, which has recently given rise to many different variations that are all attempting to, in general, solve the same problem that we just discussed. So I'm going to give an overview of the intuition behind IRM, but I just want to be absolutely clear that none of the elements of this slide are intended to be formal. The original paper itself is very informal. There's really not a whole lot of strict formality and demonstrating that the objective is like formally rooted in causal prediction. In fact, they really don't make any causal assumptions at all. So this is sort of just intended to bridge the gap between invariant causal prediction and then how this gave rise to the invariant risk minimization objective. So if we remember that we're trying to find these invariant features for deep learning. So typically the way this is done is we'll have a feature embedder phi, which learns these deep features, and we'll have some regression vector, which is like we're doing maybe logistic regression or something like that on top of the learned features. So in this case, we're going to consider linear regression. So we expect that the expectation of the target variable given these features is linear. So we're going to, again, consider the case where the data is generated according to these environments. So each of them has the same structural causal model, but they represent different interventions. And we're going to imagine what would happen if we learn some feature embedder that recovers some subset of these covariates. So remember, we won't directly observe these x's, we'll observe some complex function. But what would happen if we were to recover a phi that gives us some subset of these covariates? So suppose it uncovers the covariates x2 and x5. So remember that x5 is not a parent of y, so we might expect this to cause some problems. So to like consider this a little more deeply, in environment 1, we're expecting, we are modeling the expectation of y given the representation as a linear function of x2 and x5, which gives rise to this optimal regression vector beta 1 star. So how does this beta 1 star come into existence? What determines its value? Essentially, we can see that the functional mechanism by which x2 generates y, and likewise the mechanism by which x5 generates y, those sort of determine the informativeness of these labels with respect to y. And as a result, this gives rise to whatever beta 1 star is, right? It's some regression vector which is going to minimize the expected squared risk. So now if we consider the second environment, once again, you know, there's an intervention on the node x2, but the mechanism by which x2 generates y is unchanged. And similarly, the flow of information from x5 to y is unchanged. And so we see that the optimal regression vector in this environment is also going to be sort of whatever this vector is. So now suppose we had learned this regression vector, and at test time, we're going to be evaluating it on a new environment like environment 3. So what is the optimal regression vector for environment 3? It's generated in the same way. And once again, x2 produces y in the same way. But this time, there's an intervention on the node x4, which basically means that the method by which x5 produces y is intervened upon. And as a result, we would expect that the optimal regression vector for environment 3 is not quite the same. But the key thing is that the intervention is arbitrary, right? So in particular, if we were to use beta 1 star to predict an environment 3, we could make it perform arbitrarily poorly because this intervention could totally reverse the correlation between y and any particular feature. So we can see that when we've uncovered sort of the incorrect features, in a sense, the non-invariant features, in some environments, we can expect arbitrarily poor performance. And so we've sort of failed to recover this minimax predictor. So this sort of gives the sense that really this feature embedder is not the correct feature embedder. So we instead, you know, consider what happens if we recover x2 and x4, which in this case happen to be the direct parents of the target variable y. So we can see here that the functional mechanism by which y is generated as a function of its parents is invariant as long as y is not directly intervened upon. And recall that this is really the motivation behind invariant causal prediction in the first place. So it sort of makes sense that we would see that this is the correct set of features to uncover in the deep learning case as well. And in this case, because the mechanism is the same, we sort of expect that the optimal regression vector on top of these recovered features is the same in all environments. So this is like the key intuition behind invariant risk minimization, that if we uncover, in a sense, the correct features, the optimal vector on top of those features is the same for all environments. So like put a little bit more concretely, we expect that this expectation, in other words, the regression vector is invariant if and only if phi recovers the invariant features, which in this case is the features whose informativeness of the label like does not change across all possible interventions. So keeping in mind that this is sort of like an intuitive bridge between invariant causal prediction and invariant risk minimization, because really the IRM is not, did not present any sort of like formal connection to causality. This is sort of the idea upon which IRM is based, that the optimal regression vector should be the same for all environments. So the objective that they pose to enforce this is as follows. We can see that it's a minimization over both the feature embedder and the regression vector. We can see that this first term is basically just the standard empirical risk minimization term. We're going to ignore the possibility of like different numbers of samples per environment. So we're going to minimize the combined risk across all environments, but subject to this invariance constraint, which encodes exactly what we just discussed, this idea that the regression vector beta should be simultaneously optimal for all environments. And just as a quick side note, this is not regularized ERM. Remember that this is sort of trying to solve a minimax objective. As opposed to ERM, which sort of minimizes it in expectation over the environments, this is trying to encode this causal prediction idea. So this is the main objective that we study in this work. All of our results for this objective can pretty easily be modified, or sometimes they require no modification at all to apply to the alternatives. But this is the main objective that we'll be studying and presenting our results for. So I think this is a good time to pause and make sure that everyone is on the same page, like understands the general intuition behind IRM, keeping in mind that there doesn't need to be like a real formal understanding of the connection here.
Just a brief clarification. I understand that this is meant to be intuitive, but the invariance requirement, is it usually implemented kind of softly in the sense that there might not be a beta that simultaneously minimizes
Yes.
all of them? I mean, in the empirical sense that there won't be one. And so as long as it's close to being a minimizer for all the environments.
That's a great question. I actually meant to address that. So thank you for bringing that up. So yes, this is the official IRM objective. In practice, it's of course very difficult to solve. It's extremely nonlinear. It's like this bi-level optimization. So when it's implemented for deep learning, they have a Lagrangian form, which we study this original objective for the linear setting. And then when I discuss the nonlinear setting, I'll introduce the Lagrangian, which is meant to sort of give a soft constraint. Yeah, great question. Any other questions? All right, so I'll leave it up here on the right so you can sort of like continue to digest it as we discuss in more detail this objective. So this sort of, there are some initial problems that sort of immediately spring to mind with this objective. In particular, the original paper really only has one formal result regarding the solution invariance. As I mentioned, there's not a lot of formal ties to the invariant causal prediction paper. The formal result is more of a motivation than a justification. By that, I mean that in addition, it has a setting where it assumes that the invariance constraint is met, but then it also says some other conditions on the recovered predictor, which it's like not really clear when those conditions are met. They don't have a generative model, so it's not even clear what it means to have recovered an invariant predictor. In particular, if you recover a feature embedder that outputs the empty set, that is technically invariant according to their setting. So it's not really clear what it is that their objective is trying to uncover or what it will uncover. Their result is only for the fully linear case. It's for fully linear regression, which is great as like an initial result, but of course this objective and others are in practice being applied to deep learning. So the linear setting is obviously not applicable in that case. And so really we would like to have some sort of nonlinear guarantees with regards to how these objectives perform. And lastly, this objective, the guarantee that they give theoretically could require as many environments as the ambient dimension of the data. So for example, high dimensional images, you might expect that it's kind of unrealistic to expect us to observe hundreds of different environments. And so often it's very difficult to meet the requirements that they have for their positive result to take effect. Another issue with this formulation is that it's not really clear that expecting invariance of the expectation of y given the representation is like the correct formulation, the correct invariance to expect. This might be misspecified. So a lot of the follow-up work is based on the idea that like instead of considering invariance of the expectation, let's consider the invariance of the second moment instead of the first moment, or maybe the feature distribution as a whole is invariant. And in fact, a recent work shows empirically that really none of these beat empirical risk minimization that's been tuned properly and when they're evaluated fairly. But up until this work, there was really no rigorous analysis demonstrating whether or not these objectives uncover sort of the invariant predictor that they're searching for. And as I mentioned, we present these formal results specifically for invariant risk minimization, but all of our objectives really transfer our analysis transfers to all of these objectives. Okay, so just moving on to the latent variable model, this is a lot of setup that I've presented up until now. So now we're actually going to start going into the results for this work, although unfortunately we do need a little more setup to present the model. This is going to be like the most dense part of the talk, so I'll try to keep it reasonably high level, and at the end I'll give like a general summary, and hopefully that'll help sort of solidify everything. So we pose a formal model of the existence of these latent invariant features, which is sort of assumed by these objectives. We're going to also have this assumption of different environments, and data is generated from each environment as follows. We're going to model the label as some Bernoulli, which gives rise to these features, which can be partitioned into two sets of dimensions, ZC and ZE. And so we're going to model ZC as a label conditional Gaussian distribution, and we're going to call these features invariant. These are invariant features. Why? Because the joint distribution with the label is invariant, and as a result, the informativeness that they have of the label is invariant. So given the features ZC, the distribution of Y given these features is invariant, which sort of mirrors that causal idea that the distribution of Y given its parents is invariant. We're going to model the other features in the same way as label conditional Gaussians, but these ones are going to be environmental. And the reason they're environmental is we're going to allow the parameters of these distributions to be indexed by the environment, which means that from environment to environment, these distributions are going to change, arbitrarily. They have arbitrarily different parameters, unlike the invariant features, which are the same across environments. So this is the model of these features that we might recover. But of course, as we said, we don't directly observe these features. So instead, the observation X is generated as some generative function F applied to these latent features. So this model is a generalization of the Gaussian model, which has been used in a lot of previous work. The main distinction is that we have this generative function, so that whereas these works assume that you directly observe the latents, we're allowing for some transformation. In particular, our model allows for any invertible F. It can be nonlinear and arbitrarily complex. So this is the first analysis of these objectives and how they behave when the observations are a nonlinear function of the latent variables. So just like a couple more things, we're going to assume that we observe some finite number of environments, capital E, in our data set. But we're going to assume infinite observations from each environment. So in a sense, we have distribution access to each of the environments. And in that sense, our measure of like sample complexity for how these objectives behave is going to be with respect to the number of environments that we've observed, not with respect to the number of samples per environment. We're going to denote the dimensionality of the environmental latent space as DE, which will come up later. And in particular, this isn't an assumption, but in practice, especially with deep learning, we might expect that DE is significantly greater than capital E. We typically expect the number of environments to be on the order of 5 or 10, whereas you could imagine that the number of environmental features is much larger than that. It includes all the high frequency components that we as humans don't see. Off the top of your head, you can name like background, et cetera, all these other things. So we would expect it to be much larger than capital E. And I want to make a very key, crucial note here that this is a purely statistical model. So unlike the work in Peters et al. With invariant causal prediction, which poses this formal structural causal model, we are just modeling the joint distribution of these variables and how it can be factorized. And in particular, there's no one-to-one correspondence to causal models in the sense that, right, there's no, we can't define what it means for a feature to be a direct parent of Y here. There's no concept of intervention. Rather, we're just trying to model the idea that some of these features have an invariant relationship with Y and their informativeness does not change across environments, and other features do change across environments. So if we were to observe X and learn a feature embedder that recovers just the invariant features, then our ability to predict Y, given these features, would be invariant, regardless of what the environmental parameters are that we encounter in the future. So this sort of intuitively gives rise to the idea that our ultimate goal should be to recover precisely these invariant features. So the reason is it includes all of the available invariant information for predicting Y. But on the other hand, if our feature embedder were to recover some subset of the ZE, we would expect that at test time, there would be some sort of worst case intervention that would cause our predictor to fail arbitrarily poorly. So in particular, you should note that this model allows for a ground truth optimal predictor, right? It is the feature embedder which recovers these invariant features. And so this sort of gives a really clear formal sense of what is the purpose of these objectives. Given this model, these objectives are trying to uncover the feature embedder, which specifically recovers just the ZC. So of course, on top of this optimal feature embedder, which recovers the invariant features, we're also going to learn a regression vector, which does well. It's going to be the minimizer of the empirical risk, but because this joint distribution is the same for all environments, we would expect that it would be it would satisfy the invariance constraint of the invariant risk minimization objective. And we're going to call the combination of these two, the feature embedder and the regression vector, we're going to call it the optimal invariant predictor. It's invariant in the sense that it doesn't rely on these environmental features. And so regardless of what future environment we see, our predictive ability, our ability to predict Y will not change. And it's optimal in the sense that we extract all of the available invariant information with regards to the feature, or with regards to the label. So I know this was like kind of a dense slide. So just to give an overview, the basic idea is that we have this distinct separation of latents, one set of which is invariant with respect to the label. And so regardless of the intervention, it can't affect how our prediction fares. And one which is, you know, arbitrarily intervenable. And as a result, we sort of want to avoid it because in a minimax evaluation, we could do very poorly. So are there any questions about this model? Okay, so hopefully this is clear. Just keep in mind the basic idea is that the goal is to recover the ZC and only the ZC. And actually this model has given rise to several works already that have done like sort of follow-up analysis with this objective. Okay, so with this model in place, we can now finally present sort of the formal results that we derive for how these objectives perform, in particular invariant risk minimization. So we begin with the linear setting. Recall that we are regressing on these learned features Z hat, which is our feature embedder applied to the observation. And we're going to restrict the generative function f to be linear, and it's also invertible, which basically means that we can learn a linear feature embedder phi, which will invert the features, and then we could, you know, zero out the environmental features. So phi as a linear function as a hypothesis class includes the optimal invariant predictor. So with this linearity assumption, our features can be written as a linear function of the two different sets of features. So in particular, any choice of phi induces a learned feature set, which is a matrix A times the invariant features plus B times the environmental features. So as we mentioned before, if we want feature invariance such that we have this sort of mini-max optimal approach, our goal should be B equals 0 in the sense that we don't want to use the environmental features whatsoever for prediction, because if we do, then an intervention could cause us to perform poorly. On the other hand, to capture all the invariant information, we sort of expect that A should be full rank. We want to extract all the information available that will not cause us to fail. So keeping this in mind, our main result in the linear setting is as follows. Suppose we observe capital E environments, then if the number of environments observed is less than or equal to the latent environmental feature dimension, then there exists a feasible linear phi, which means it satisfies this invariance constraint, which induces a B that has non-zero rank. In other words, it extracts information from the environmental features, and as a result, it is not a minimax predictor. It could be made to fail just like ERM. And finally, this phi that we've constructed will also have lower training risk than the optimal invariant predictor. So this means that, you know, subject to the constraint that we are solving this objective, this particular feature embedder that we've learned will be preferable under the IRM objective to the optimal invariant predictor, which you'll recall is sort of like the gold standard. It is precisely the ground truth that we are hoping to uncover. So this sort of shows that, like, if you observe a number of environments that's less than this latent dimensionality, then even if we could correctly optimize this objective, what we would uncover would sort of fail just as poorly as ERM. On the other hand, we can also show that if the number of environments is greater than the latent environmental dimensionality, then any phi that satisfies the invariance constraint must have B equals 0. And as a result, it only uses the invariant features. And in particular, the optimal invariant predictor, as we mentioned, uses as much of the invariant features as possible. So as an immediate corollary, we have that the optimal invariant predictor, which is sort of the ground truth that we're seeking, is the global minimum of the IRM objective, if and only if the number of environments we have observed is greater than the number of latent environment dimensions. But recall that we expect DE to be significantly larger than E. So while this is technically both a positive and negative result, in practice, we would typically expect the negative result to apply. So I'm gonna give a brief proof sketch and then sort of like a comparison to the invariant risk minimization paper. But before I do, are there any questions about sort of like what this theorem is saying?
I think this is a very interesting result. I'm assuming you've thought about the connections to like sparse regression, lasso kind of results where if you're looking for something deterministic, like this is like a deterministic statement, like if and only if, and there isn't any probability, then you have these harsh conditions for being able to recover exactly the support of a sparse vector. But then if you resort to randomness, and if you were somehow able to design your environments randomly, then you could hope that maybe, for example, with some kind of logarithmic dependence on the ambient dimension, you might still escape. Do you think something like that's possible?
Absolutely. I have, this is something that I'm actively thinking about. And you're absolutely right that if we sort of allow for a little more randomness, then you would expect we could show like less of a dependence. But one additional thing that I want to note is that we have an additional result, which I actually haven't included in this presentation, which is that it's not just a matter of whether or not you recover the optimal invariant predictor. In fact, we show that there are predictors that depend exclusively on environmental features that are more preferable under the IRM objective. So in a sense, it's not just that like you don't get precisely this objective, it's that you will most likely fail catastrophically and like not even get close to the OIP unless you have enough environments. But that's a really good point, and this is an active area that we are looking into.
Thank you.
Yeah. Any other questions? Okay, so just a very brief proof sketch of how this works. We should first note that if we learn a feature embedder that recovers all of these invariant features, and additionally extracts some more information from the non-invariant features in the sense that B is not equal to 0, so right, it includes some information about ZE, then we would expect that the predictor, the regression vector on top of this would have lower risk than the OIP because we're taking advantage of additional information about the label Y. But then what remains to show is that any phi, right, the intent of IRM is that if B is not equal to 0, it won't satisfy the invariance constraint. So basically the proof here is to show that there exists a phi with B non-zero that will satisfy that constraint. So we note that with the F and phi as linear, this means that the sort of inferred latent distribution is Gaussian. And so the optimal vector on top of these learned features is available in closed form. And in particular, this can be expressed as a function of B. So whatever B our phi induces, we can express the optimal vector on top of it as a function of B. So the goal now is to construct a B which will be non-zero, but also have the same optimal predictor on top of all different environments. So we explicitly construct this matrix as a function of the environmental parameters such that it has this rank, which is greater than 0, so long as the stated condition holds. And what this means is that our predictor will depend on non-invariant features. As a result, it'll have lower risk, but it won't be minimax. And simultaneously, this beta star that we've solved for in closed form is going to be equally simultaneously optimal for all environments, and therefore it satisfies the IRM constraint. So this is the failure case of IRM. But then in the reverse case, we show that if you have enough environments greater than DE, then any B which induces a beta star which is invariant across all environments necessarily must have rank 0. So it has to be the 0 matrix. So this is the general outline of the proof. The main takeaway is that invariant prediction in the linear setting, it's technically possible if you have enough environments, but it's very difficult. It seems very unlikely that in practice we would get enough environments. And in particular, this linear dependence seems unavoidable without, as Aditya mentioned, these potentially stronger like randomness assumptions.
I have a quick question. Yeah. What's on the previous slide in the proof outline is like a high level idea that sigma is low rank, and so you can have B being in the orthogonal subspace.
So we actually allow for full rank sigma. The basic idea is that because you can solve for beta star as a closed form function of B, each observation sort of restricts the dimension of the space that beta star can lie in if B if B is non-zero. And then once you observe more than the number of latent dimensions, you basically restricted it to the null space. Okay, so this is the main takeaway. The IRM paper has a similar upper bound in the sense that they show a positive result. Again, it's kind of like unclear what exactly the result is saying. It doesn't really, there's no generative model that they pose. Our bound is sharper in the sense that we explicitly only require up to the latent dimensionality, whereas, as I mentioned before, theirs could theoretically depend on the number of dimensions of the observation space. Our bound is also a little bit more easy to understand because we have this clear tie to the generative model that we're posing. So it's like very directly observable what it is that we are recovering. We also give a matching lower bound. This is the first lower bound that's been given for any of these objectives. So the IRM paper comes with this guarantee that if you meet all these requirements, A, B, and C, then you will uncover a predictor. And one of them is you have to observe enough environments. But until now, there's been no analysis saying what happens if you don't observe enough environments? Will you still do reasonably well? And our work shows that the answer is actually no, you won't. So as I mentioned, both of these proofs show that each observed environment restricts a degree of freedom of this feature embedder phi until you've restricted them all. So the natural next question, which is also sort of posed in the paper by Andrej et al., is does this intuition extend to nonlinear observations? Can we also apply this in the case where we're doing this for deep learning? And will it be the case that after we observe enough environments, we will sort of do better in a minimax sense than ERM? So now we move on to the nonlinear case. I think I don't have enough time to go into the proof sketch, so I'll just present the result itself. Just as setup, recall that we are regressing on these learned features Z hat, but this time F and phi are arbitrarily complex. In particular, they're nonlinear. In practice, phi would be implemented as a deep neural network, extracting these features for classification. And so as we foreshadowed earlier, it's really difficult to solve this objective, like actually solve the constraint. So instead we study the Lagrangian, which is also introduced in the IRM paper, which is known as IRM v1. So it replaces this constraint on the regression vector with a penalty on the squared gradient norm of the risk in each of the environments. So you can see the connection here is that if the risk is convex, then beta is optimal in a given environment, if and only if the gradient is 0. And as a result, if we take lambda to infinity, these two constraints are equivalent. But of course, when we actually implement this, lambda is not infinity. So when we run it, we're basically solving it until the penalty is reasonably small. So our main result in the nonlinear setting is as follows. For any invertible f, arbitrarily complex, we're going to construct a predictor, which is going to consist of the feature embedder phi and the regression vector beta with the following property. So similar to the linear case, we're sort of constructing this fake predictor, which could be uncovered, which is preferable, either preferable or we might reasonably expect to uncover with the objective, but performs poorly at test time. So we're going to refer to this predictor as the fake predictor. So I'm going to basically just run through the results, and then I'll go back and give a high-level intuition for what these individual items are saying. So for this fake predictor, the penalty term is exponentially small in the environmental latent dimension. Furthermore, the fake predictor matches the optimal invariant predictor on all but an exponentially small fraction of the training data. And finally, at test time, if we observe a test distribution that's slightly different from the training distributions, this is of course stated informally, then this fake predictor that we might uncover behaves exactly like ERM on all but an exponentially small fraction of that test distribution. So just going back and sort of parsing what each of these are saying. These first two statements are saying that for any generative function f, there's a predictor which is practically indistinguishable from the OIP at train time. And in particular, remember that we are assuming an infinite number of observations from each environment. But if we were to instead assume something like polynomial number of samples, like a sub-exponential, then item 2 says that our predictor is exactly equivalent to the OIP with very high probability on all the training data that we've observed. So in a sense, if we don't have infinite environmental samples and we have sub-exponential, it's very likely that this fake predictor will be literally indistinguishable from the optimal invariant predictor. On the other hand, at test time, this predictor, which we very well might uncover, will perform almost exactly like the predictor learned with ERM. And in fact, if we observe fewer than exponential samples at test time, then it will behave exactly like ERM, which basically means it will suffer from exactly the same drawbacks as ERM, which recall was exactly the intent of these objectives. So this objective also easily extends to all of these alternatives that have been proposed to IRM. So the main idea is, remember, even if we could solve these objectives, because again, these are very nonlinear objectives that are difficult to solve, but even if we could solve them, there's really no reason to believe that the features we've uncovered or the predictor that we've uncovered will do better than ERM. And this is such a powerful result because this is really the first result in any sort of nonlinear latent variable setting that analyzes how these objectives perform. So we've basically shown that, actually these don't achieve the goal. And as I mentioned, with little to no modification, this applies to all of the alternatives. One additional thing to note is that you might expect there is sort of a setting where these objectives would work. And that is if we assume that we observe enough environments to essentially cover the space of features. Because recall that we say that it fails on a test distribution that's different from a training distribution. So if we were to observe enough training distributions that any test distribution would be reasonably close, then we might expect it to perform better. But then again, this is exactly the same thing that ERM could leverage to perform better, right? The reason ERM fails is because the observed data is very different from the training data. But if we were to just run vanilla ERM and we observe, say, an exponential number of environments to cover the full space, then clearly these invariant objectives don't really provide like a performance guarantee or a sample complexity guarantee over vanilla ERM. Okay, so are there any questions about the result in the nonlinear setting?
A very quick clarification question. So it seems like you want to relate the OIP to ERM, and you do it by constructing this middle guy and say that OIP is similar to the middle guy during training, and the middle guy is similar to ERM on test.
Exactly.
And is that?
Yeah.
Okay.
We construct this guy that like at train time looks just like the OIP, and then at test time looks just like ERM. So basically, we might as well just be doing ERM.
So
there. Clarification. Oh, sorry. Go ahead, Adi.
No, it's fine. Go ahead.
I just had a quick clarification about the last point here.
Sure.
Suppose that you were in a setting where you would really not want to use IRM potentially, or where you would expect to get the exact same thing as ERM. So you have maybe multiple environments, but they're all the exact same environment. Is what you're saying here, are there provably sort of any, like what would the potential computational or statistical inefficiencies be in using IRM in that setting? In a setting where, maybe you would think about not using IRM because all the environments are really the same. Can you say that there's any inefficiencies to using IRM in that setting, or?
Yeah, I mean, it's, remember that it's like this extremely, it's not clear basically how to solve this Lagrangian correctly. There's all sorts of work, like follow-up work that considers, okay, well, we want to start with lambda small, and then at the optimal point during training, increase it to like a very large number. There's really no analysis of like statistically, what does it mean to try to solve the IRM objective or computationally, as opposed to trying to solve just vanilla ERM. I would expect that it's, when we're dealing with a very nonlinear model like a neural network, it's probably not significantly easier or harder. But in practice, when you're training the IRM objective, unless you, I'll actually touch on this at the end, unless you sort of tune on the test set in a sense and like pick the optimal hyperparameters, it frequently collapses to the ERM solution. So like even while you're trying to solve this different objective, whatever effect it has on your like optimization trajectory, you usually or often end up at the ERM solution. But I'm sorry, I don't really know, like with regards to the actual computational difficulty, if it makes a big difference.
Okay, okay, interesting, thanks.
Okay, so this is really the main takeaway from this paper. This nonlinear setting is like the fundamental result that we present, that when you're considering these objectives for deep learning, really there's no reason to believe that IRM or any of these objectives will do better than ERM at test time. So it's kind of like we need to be considering other things. So what is the basic takeaway that you should walk away with from this presentation? Causal reasoning, to be clear, this is maybe a little bit of my sort of like subjective opinion. I think that causal reasoning is a really promising approach for invariant prediction. This invariant causal prediction paper by Peters et al., which was grounded in rigorous proofs for identifiability, I think it's a very promising approach for this sort of out of distribution generalization. But when the features are latent, we can't just like haphazardly slap on this objective with a deep objective and hope that we'll recover the correct thing. It really requires a lot more care, especially when we're dealing with high dimensional images that we might expect a nonlinear function of some hidden latents. Also, and this is going back to the question that was asked, we need to stop tuning on the test set. This is something that has actually become like persistent in all of these follow-up works, that they present results as sort of like a proof of concept, but actually what they've done is they've used the test set as a validation set to find the optimal hyperparameters. And as I mentioned, the work by Gulrajani and Lopez Paz showed that in a fair setting where you don't cheat, none of these objectives outperform ERM empirically. So this work sort of presents the theoretical corroboration for that observation. So some open questions that remain, as Adi was asking, is there any way to sort of avoid this linear dependence? And yeah, with the right assumptions, with the right setup, root DE or even log does seem feasible. So this is a very interesting open question. And then in the nonlinear case where it's a lot more difficult, is there anything at all that we can do to improve over ERM? And one promising direction I think would be to consider limiting the complexity of phi. That might allow you to sort of show these provable guarantees for recovering the correct invariant features. So thanks so much for coming. Thanks again to my advisors and co-authors, Pradeep and Andrej. Are there any more questions?
Yeah, I see people clapping. So let's clap. Is there any question or comments?
I find the connection to data augmentation really interesting. So I was wondering if you could speak to like, what is the dimensionality of like what you call DE, and then what if we were to just augment the data so that we observe more environments than DE?
Yeah, so this is, I think, at an intuitive level, this is something that people have already been working on for 5-10 years. Like, obviously, we expect that the rotation should not change what the image is depicting. So we're going to induce invariance to the rotation feature by rotating the data set. But then as a question of like, can we formally show that these variations induce invariance? Of course, the theory always lags behind a little. So there's recent work on sort of provable improvements as a result of like group theoretic modifications. And there's a study in like contrastive learning of like what is the correct modification to be doing to induce invariance to the features which will not be informative necessarily of the label in a downstream task. So this is like a very active area that's like I'm very interested in, that I'm continuing to work on.
Yeah, it's cool.
I guess in the setting of contrastive learning, you don't have the labels, right? Which makes things a little bit different.
Yes. Yeah, absolutely.
All right. Any other questions from the audience? Okay, then. Well, let's thank Elan again for this amazing talk. I learned a lot, definitely. Yeah, as a reminder, we're meeting at the same time next week. We're going to have Noah Smith from the University of Washington talking about some recent progress in language modeling. All right, if there's no more question, thank everyone. And thank you, Elan, for attending the seminar today.